Numpy broadcasting is one of those rare features that feels completely natural when you use it, yet quietly powers some of the fastest and most memory-efficient numerical systems in Python. It allows developers to write code that looks simple, mathematical, and readable, while still scaling to massive datasets. Most of the time, broadcasting works so smoothly that it fades into the background. But behind that smooth experience is a carefully designed mechanism that fundamentally changes how numerical programs are written, reasoned about, and scaled. Many developers encounter broadcasting accidentally. A vector is added to a matrix, the result appears instantly, and nothing seems unusual. There are no loops to write, no dimensions to manually align, and no warnings to interpret. Because it just works. We accept it and move on. But that moment, when arrays of different shapes combine without complaint, is the first sign that Numpy is doing something far more sophisticated than it appears. Broadcasting is not a shortcut, it is a deliberate design choice. Before broadcasting existed, numerical Python relied heavily on explicit loops. Each iteration passed through the interpreter, checked types, and accessed memory repeatedly. As datasets grew, performance collapsed. Numpy changed this by introducing contiguous memory layouts and vectorized operations, pushing computation into optimized C code. Broadcasting emerged as the next evolution, a way to preserve vectorization even when real-world data did not arrive in perfectly aligned shapes. It allowed developers to express intent, while Numpy handled alignment silently and efficiently. What makes broadcasting special is that it removes noise from numerical code. Instead of writing logic that explains how to line up data, developers focus on what relationship they want to express. The result is code that reads closer to mathematics than to control flow. For teams building analytical platforms, simulations, or data pipelines, this clarity is not cosmetic. It directly reduces bugs, simplifies reviews, and makes complex systems easier to understand. Yet broadcasting is also one of the most misunderstood features in Numpy, precisely because it is implicit. There is no function call announcing its presence. As long as shapes are compatible, Numpy quietly aligns them. When misunderstood, this silence can be dangerous. Developers may unknowingly rely on assumptions about shape alignment that break later when data changes. The most serious broadcasting bugs are not the ones that crash, they are the ones that silently produce incorrect results. Broadcasting does not resize arrays, and it does not copy data. It defines how Numpy interprets shapes during element-wise computation. Smaller dimensions of size 1 are conceptually repeated, while larger dimensions remain unchanged. The output shape is determined predictably by aligning dimensions from right to left. Although it looks like data is being duplicated, no actual duplication occurs. Numpy reuses memory through stride logic, making broadcasting both fast and memory efficient. This illusion of expansion is the key to broadcasting's power. Without it, combining arrays of different shapes would require allocating massive temporary arrays, quickly exhausting memory. Instead, Numpy performs the operation directly, using the same underlying data. Once the computation finishes, the original arrays remain unchanged. This guarantees safety, predictability, and performance, all at the same time. In production systems, broadcasting is not a convenience feature, it is an architectural tool. Teams that understand it deeply write fewer loops, allocate far less memory, and ship faster. Broadcasting often determines whether a system remains stable under load or fails unpredictably as data scales. At Thunibit, we use broadcasting daily to design Python systems that remain fast, readable, and maintainable even as complexity and data volume grow. Broadcasting reflects a core Numpy design philosophy: push computation into low-level optimized routines while keeping the Python layer expressive. Developers should think in terms of mathematical relationships, not memory layouts. This philosophy allows the same code to run efficiently on a laptop during prototyping and scale seamlessly to enterprise or scientific environments without rewrites. Experienced Numpy developers don't guess how broadcasting will behave, they reason about it. They think in shapes. They ask which axes vary and which remain constant. This mental model makes broadcasting predictable instead of mysterious. Once this shift happens, debugging becomes faster, code reviews become easier, and numerical logic becomes easier to explain to others. Mastering broadcasting is a turning point in Python engineering. It marks the transition from writing code that merely works to designing systems that scale. Teams that understand broadcasting write cleaner APIs, reduce transformation stages, and avoid unnecessary memory pressure. If your organization is building data-intensive Python solutions and wants performance without sacrificing clarity, Thunabit helps teams turn deep Numpy knowledge into real-world, production-grade engineering success. Broadcasting is not magic. It is a disciplined, well-defined system that rewards understanding. Once you see it clearly, Numpy stops feeling clever and starts feeling dependable. And that confidence, the ability to reason about performance, memory, and correctness before code even runs, is what separates working scripts from truly scalable Python systems. As we wrap up, it's important to see Numpy broadcasting for what it truly is. Not just a feature, but a mindset. Broadcasting lets you focus on expressing relationships in data instead of managing loops, memory, and alignment. That shift is what turns ordinary numerical code into scalable, high-performance systems. When you understand broadcasting, your code becomes clearer, faster, and more resilient. Large datasets feel manageable, shapes feel intentional, and performance comes naturally because Numpy does the heavy lifting in optimized low-level code. What once required complex logic becomes a single, elegant expression. This is why broadcasting sits quietly at the heart of modern data science and scientific computing. Teams that master it build systems that scale smoothly and fail less often. At Thunabit, we help organizations develop this level of Python engineering maturity, transforming powerful concepts like broadcasting into reliable, production-ready solutions that grow with your business. And if this overview sparked your curiosity, there's much more waiting for you. We've only scratched the surface of what Numpy broadcasting can really do in real-world systems. To explore the concepts in depth, walk through practical examples, and see how professional Python teams apply them at scale, visit our blog using the link in the description. Our blog features a rich collection of in-depth articles on Python, data science, scientific computing, and high-performance engineering, written from real industry experience. If you're serious about building faster, cleaner, and more scalable Python solutions, that's where the full story continues.